Discovery's 4 computers now have primary control of critical vehicle functions.
All right, everyone, welcome to today's ASRG webinar. But before we get started, I'd like to tell you a little bit about ASRG and get some of the legal stuff out of the way. ASRG is a nonprofit organization founded to support the development of the automotive security industry. We have developed a platform and a community to share knowledge, communicate through networks, and to build value with collaboration. This is a community for you, built by you, with the goal to protect our friends and family when using automotive products. If you want to learn more about ASRG or get more involved, please visit our website at www.asrg.io or send us an email at hello@asrg.io. Before we jump into the presentation today, let's get some of the legal stuff taken care of. The views and opinions expressed in this webinar are the views of those that have made them. They do not represent views or opinions of ASRG and are to be considered as informational. The use of this information is to be used by the individual and/or organization at their own risk.
Good morning, everyone, and welcome to this Automotive Security Research Group meetup. My name is Olivier Korach. I'm a technical pre-sales at TrustInSoft, a leader in static code analysis based on formal method. And today, precisely, I will speak about application of formal method to high security requirement software. So in terms of agenda, we'll cover the following. First, we'll speak briefly about the story of formal method and describe a little bit what it is. And then we'll speak about why using them. And then we'll compare that with a couple of other techniques like unit test and fuzzing, because sometimes it's not really clear to understand how a formal method differentiate from that and bring additional value. Then we'll speak specifically of embedded software and why formal methods are particularly useful in that space. I'll give a couple of industrial examples. Then I'll discuss about the link of formal method to a safety and security standard that may be required in your particular industry. Then I'll discuss about the integration in development workflow, because more and more we want that tools integrate mostly in such thing. And then I will wrap up. So history of formal method really quickly. Well, even though you can certainly find traces of formal methods before this time, one can consider that really formal methods emerged from academic research in the 1990s. Originally remaining in university, but the first industrial application came sometimes later, around 2005, where we have seen such technology used in critical industry like aeronautics and energy software validation. Why only in those industries? Well, principally because at the time formal methods were relatively complex to use. You had to have some sort of understanding of how they work, some experience in it to be able to use them. So why those industries would use them anyway? Well, because it allowed unmatched software validation at a much lower cost than with traditional techniques. So for those industry where the depth of validation is of utmost importance, it was okay to accept the downside of complexity, I would say. But the technology has evolved. Of course, there was a move to make such technology more usable for the average users, let's say. And in the middle of the 2010, around 2015, we have seen the first general purpose formal method product hitting the market. And as of today, in 2023, one can consider that formal methods is now a mainstream technology. It provides a new innovative approach to static code analysis. There have been a static code analyzer on the market for a long time, but with the approach of based on formal methods, you have a much more exhaustive analysis, going deeper and capable of finding more complex problems that may be missed with traditional tools. To make its success as a mainstream technology, it had to become easy to use. This is the case. To integrate with some standard development workflows. And beyond safety and quality, which was the original target in those industries I mentioned before, aero and energy, it is now a perfect match for security because it's more or less the same problem. Okay. Finally, the industry that are targeted by formal methods are embedded software, and those technology prove to be perfect for such a market. So, what are formal methods? Well, in particular, if we compare with traditional static code analysis, it's important first to keep in mind that formal method is all about mathematics. For formal method-based static code analysis is a concentrate of math. The second thing is that it's not one, but it's a collection of techniques. One can cite abstract interpretation, model checking, dependency analysis, SMT, satisfiability modulo theory, weakest precondition, theory of proving, and many more. And that typically when you have a formal method-based tool, you will not rely on a single but multiple of those technology, and the way you mix and match those technology finally define what is the final value that's delivered by such tool. Okay. What is also interesting and important to mention about formal methods is that it can prove two things when speaking about source code. It can prove the technical correctness of your code, meaning that your code does not define any statement that are likely to cause a runtime error or to fail for some reason, like a division by zero, like a null pointer dereferencing. I would say that's the first stage of a formal method, and it's already quite useful. And the second thing is that it can prove the functional correctness of your code, meaning that not only the code is free of any technical errors, but the logic of the code corresponds to the functional specification of it. Okay, so what are the benefits of using a formal method for static code analysis? I will start by the second bullet point. Really the main and the first benefit is that it provides much deeper analysis than with traditional rules-based techniques. Because of this particular property, it's particularly suited for software development projects with high security requirements. Now, with formal methods, you have the guarantee of zero false negative, meaning you won't miss any of the types of problems that can be detected by formal methods. It depends if you target technical proof or functional proof. And also conversely, you have no to very few false alarm, because we know false positive is something that is really a plague in the world of traditional static code analysis. And speaking of the properties that are all equivalent compared to traditional analysis, now with formal method-based tools, you have exactly the same capability. Formal method tools are developer-friendly, are easy to use, they are easy to integrate in CI, and I would say they are on par with traditional tools. So, why using formal methods? All right, so I hope that the previous slide and the teaser promise that of what formal methods could deliver in the world of static code analysis was already sparking your interest. If we look in more details on the needs that are well addressed by formal methods, first of all, in the embedded market. It's a market where time is of essence more and more. I would say a couple of years ago, the cycles were long and once for all. Now it's shorter cycles with a constant delivery. The embedded software development is on acceleration. You develop more software faster. And being one of the first on the market in a particular segment can be a strong competitive advantage by taking the lion's share of that market. So developing and validating software quickly is clearly an advantage. The second is cost, like in any software development environment, but embedded more than others. The cost shall remain in mind of whoever develops something. And thanks to formal methods, you can lower your cost and develop faster and validate your code faster than what you can do if you were to use traditional techniques. The last aspect is compliance, because many standards you may have to comply in safety or security world required to meet a certain number of criteria. And we'll see, I don't want to spoil that, but several standards mention formal methods as being an excellent means to achieve compliance. Finally, it's security, because beyond safety, if you want to deliver secure software on the market, formal methods are an excellent way to guarantee absence of vulnerability in your code. All right, so now I will speak about the positioning of formal method, meaning proving things, giving technical proof or functional proof versus testing, because sometimes when you discover formal method, the relative contribution of those two activities is unclear, and you may believe that they overlap. To explain the difference between testing and proving, I will use a simple equation like this one: a plus b squared equals a squared plus b squared plus 2ab. Let's say that I want to verify that this equation is true. Okay, I can have either a testing approach or a proving approach. If I want to do that through testing, the idea would be to test for many values of a and b, let's say 1 and 3, so 1 plus 3, 4 square equals 1 square plus 3 square plus 2 times 3, then I try another value, then another value, etc. Even in the world of computers where integers do not have an infinite range, just an extra large, that's already an enormous number of combination. I can sample that, but I cannot prove that this is true for all integers. And oh, by the way, integers are not alone. This is something that I want to prove also for floating point numbers. So I would have to do the same exercise for another enormous set of input range, which is completely impossible. Even if you help yourself with a fuzzer, something that will massively inject inputs into your code, you will only cover a fraction of the possibilities, so you will not prove that this is true for all cases. Okay, so the second option now is really to prove that, and this is what you can achieve with formal methods. So instead of testing with a couple value, you will do an algebraic proof of what you want to prove. So you will expand a plus b square, you will do all this math, and you end up with this final value of a square plus b square plus 2ab, and done. This is proven for all possible value of a and b regardless of the input space. Software. Let's take another example. If you want to calculate the hypotenuse of a right triangle, and that you want to make sure that your function calculation is correct, let's say I've written an hypot function with two parameters, the a and b sides, and I want to compute the hypotenuse. I can verify that with 3 and 4 the value is return is 5, that with 12 and 35 is 37, etc., etc. Okay, but I cannot test all the possible value. It's gonna be a finite set all the time. Okay, if I want to do an exhaustive proper implementation, okay, so I want to see that functionally it will always return the right result, I will have to do that with all values of positive floats a and b, okay, and if you want to do functional proof, it will also help you raise the corner cases. What if you exceed the the range of possible floats, double max, which is the largest possible floats. I will have to handle it correctly. What if the inputs A and B are negative? Yes, there should be an exception also, etc. So that's really the difference between between testing and between making a proof of something in that particular functional proof. Okay. So the above here is unit testing, and it's perfectly a good activity, but it's different than achieving functional proof, which is the second part. All right, so now let's focus a little bit more specifically on the technical proof on the code, and more specifically on the C++ language. I'm spoiling it a little bit, but in the future we'll see that we'll spoke mostly of those languages because these are the ones that are used in the embedded market. Means to make a technical proof of a program written in that language. It's to prove the absence of undefined behavior in the code. What are undefined behavior? It's a bit of a cryptic name. It's all sorts of runtime errors. They are probably more well known under this name. Specifically, one can cite plenty of very well-known types of undefined behavior, like buffer overflow, area index of out of bound, invalid pointer usage, pointer dereferencing, dangling pointers, usage of non-initialized variables, or in the field of arithmetic operation, integer overflow, division by zero, float to int conversion overflow, etc. There are plenty of them if you look at the standards. More than 100 of them, and all those are technical error or runtime error that can happen in your code. And if you want to make technical proof, it means proving not just a best effort detection, but proving the absence of such error in your code. Why this is important? For several reasons. First of all, they can lead to a disastrous consequence in your code, software misbehavior or crash, unpredictable outputs or unpredictable program execution. And in the field of security, this is a main vector of cyber attacks for program intrusion to allow arbitrary code execution and the likes. And one can state that the majority of attacks resulting in arbitrary code execution in C++ code are due to undefined behavior. The other aspect of this is that undefined behavior are complex problems. They may not materialize immediately. They may have an effect after the fact, and they are extremely difficult to detect. So having a tool that can detect them without any ambiguity and without any risk to miss one is quite important. You may wonder, okay, now I understand undefined behavior, things like buffer overflows or integer overflows. If you are in the domain, maybe you already realize how important that can be, but if you are not, let's look at a certain number of undefined behaviors on the past and their impact on their business impact. The first example I'll give is the Ariane rocket, space rocket, where a float to int conversion overflow failed because the float value could not fit in an int, and it led to a cascade of events that resulted in the loss of a rocket. So the impact here is numbered in hundreds of millions of dollars and severe delays in the Ariane spatial programs. Okay, another example, again also related to Softy. It's an integer overflow in that case. The software counter internal to the generator control unit of the Boeing 787 Dreamliner overflows every 248 days. That's exactly the time it takes to reach the maximum integer value if you tick every 10 milliseconds. Okay, and because of that, the Dreamliners have to be grounded and switched off and reset every 248 days at the maximum to avoid the plane main GCU to lose electrical power after going to in failsafe. So you see here, that's more an impact in terms of maintenance cost and potentially also in reputation for the aircraft manufacturer. Let's look now at cases in the safety space. So one coming from an important tier one of the automotive industry, where a buffer overflow in the temporary mobile subscriber identity component provided by this vendor could allow an attacker to access and control memory and achieve potentially remote code, arbitrary code execution, stealing data on the vehicle, etc. And because of that, the impact was that even if this was probably not exploited, or we don't really know, but preventively, several car makers had to shut down temporarily their TCU module on some of their model to not be exposed to the issue, which means that yes, for sometimes the software could not be updated on the vehicle. The second one is also interesting. It's from Realtek, a provider of IoT components, and because of a buffer out of bounds write, this could allow arbitrary code execution, and this one was exploited. As a result, more than 130 million IoT devices were hacked worldwide, exploiting this vulnerability. Finally, WhatsApp. There are many of them. One is an example here. A buffer overflow in the WhatsApp voice over IP stack allow remote code execution once again on mobile phones, and because of that, attackers were able to deploy surveillance tool on the device. So again, I don't think from a consumer market perspective, being spied or surveilled is a good feeling, and reputation on WhatsApp was affected because of that. So now I said it's important that the tool to be democratized and easy to use to provide let's say a smooth adoption path to tools based on formal method. This path that I will expose now is a little bit based on our own tool. I don't know if there's such things in alternative solution. And really, this path is meant to ease the learning curve of a formal method-based tool for whoever has had the experience of traditional static code analysis before or no experience at all. So we provide this journey, which is based in three steps, where each step or the initial steps are really easy, making the first adoption simple, and then progressively you can go deeper and also get more value. The first step is called the interpreter mode, or level 1, and this one is really very easy if you already have unit tests, because it's simply or unit test, I should say, test in general, because you simply replay test with the analyzer, the input of the analyzer being test, because we do symbolic execution of the code. Okay, and what's the value, you may say? But simply because tests are typically relatively functional and they may miss robustness or reliability problems, that will be deterministically found by the TrustInSoft analyzer. Okay, so immediately by replaying your test, you are likely to detect bugs and vulnerability that were missed by your traditional unit test framework. You get mathematical guarantee, meaning that you are certain that all the problems that may remain in your code will be found, okay, for all the inputs that are chosen in your unit test. So you get 0 false positive and 0 false negative. All the problems found are truly problems. And by the way, since we focus on bugs and vulnerabilities, your developers will not be flooded by thousands of issues. In general, we are quite selective, and we report real problems, but not too many of them. Once you're fine with this step, or once you are ready to go to the level 2 of our product, which is called analyzer mode, you can do that, and it provides an important increment in terms of value compared to level 1, because it will allow you to generalize your inputs. So meaning, instead of testing your code with a finite set of input vectors that you may have chosen from your test, or based on your reflection on what are the meaningful value to try to be as exhaustive as possible with your test, you will perform the equivalent of test for all the possible inputs. Okay, so suddenly you are completely exhaustive, and you will verify that the code that you are validating is robust to any possible input value, which is obviously a more compelling or a more certain proposition than trying to be smart and guess what are the interesting inputs to verify. Okay, so when you do that, still you get this mathematical guarantee that we will find, or that formal method will find all the problems, the robustness problem in your code. Again, we call them undefined behavior. Okay, with 0 false negative, we find all the problems. We don't miss any. At this stage, there might be a low rate of false positive, lower than with traditional static code analysis techniques, but not necessarily always the promise of 0 false positives. Okay. Thanks to this approach of generalization, also the nice side effects is that you are likely to exercise more branch of your code, because you try all possible inputs. So you are covered on 2 dimensions. First, input coverage and testing all the values. And secondly, code coverage, potentially reaching to 100% of your code when your code is particularly critical and you want to make sure it's extremely well covered with your validation. Once you have done that, there's let's say the golden solution, that is functional proof. That's a superset of the technical proof. This is quite interesting for supercritical software, but also quite demanding. There's an investment, a human investment in terms of specification that's necessary for this step, which is much higher than the first 2 levels. And by experience, I would say probably 90% of the market does not need the functional proof, or the effort involved in functional proof is too high compared to the value and the requirements for the software. So I would say 90% of the market is only using level 1 and level 2. Okay, but when that's necessary, and very specifically on the pieces of code that you want to validate extremely well with functional proof, this is something that you can use with formal method and with the TrustInSoft analyzer in particular. Okay, I already spoke about it a little bit, but what's the difference between testing and proving? So remember what I explained earlier, and this diagram shows fairly well how all of this is related. Unit tests are mostly behavioral. They test nominal case, and they may also include edge cases. They track algorithmic error, so they will verify that the output of a particular function is the one that's expected for a given input. TrustInSoft robustness proof, so level 1 and level 2, is mostly robustness. It tracks technical errors, both in nominal and edge cases, and will verify that in the course of execution, not that the result of a particular computation is correct, but that in the course of execution, there is not a statement that causes an undefined behavior. And then level 3, which is functional proof, encompass everything. It covers the functionality of unit tests for functional proof, and of TrustInSoft level 1 and level 2 for robustness proof. So let's speak about a little bit about generalization to realize the value of this. Let's take the example of a function that takes an integer as input. That's already on a 32 bits CPU, 2 to the power 32 value. So if you wanted to test all the values one by one, that would be the equivalent of 4 times 10 to power 9 tests. That's around 4 billion. That's already quite a lot. That's already probably out of reach of traditional testing. But yeah, very often you don't have a single parameter. Let's say that you have 2. Now the problem becomes 2 to the power 32 to the power 2. So that's 2 to the power 64 input value. And that's the equivalent to a very large number that I can't even name. That's trillions of trillions. And let's go to an even more realistic case where you take 2 integers, a double on 64 bits, and a buffer of 1024 characters. Now the number of tests that you would have to do if you wanted to test all combination is an astronomical number that is completely unreachable. And that's the promise of formal method generalization, where you will be able to perform the equivalent of such a large number of inputs, tests for such a large number of inputs. Okay, so and this is absolutely not a brute force approach. It's using mathematics. Each variable will hold an interval of value, so it's all completely doable. And the execution time is not related or not proportional to the number of test equivalent that we do. It depends on other factors, but not on the input, the number of input vectors. Again, to explain the difference between testing and TrustInSoft technical proof and why it is important. Let's take the 2 examples that will explain the differences, and both are complementary. If I take the increment short functions here, that takes a short as input and returns an integer, and if I implement it as return I plus 2, probably the functional specification of this function was to increment by 1. So if I run it with unit test and I verify that if I give an input, I receive the input plus 1 as output, I will notice that this function is behaviorally incorrect. So if I do test increment short of 3 and I verify it's 4, it will fail and I will detect the error. Technical proof in that case will not raise any issue because it doesn't know what should be the functional specification of this function, and the behavior or the execution of this function would not cause any undefined behavior. Okay, because I get a short as input, so probably an integer on 16 bits. I return an integer on 32 bits, so even if I take the largest 16 bits integer, I can increment by 2 and get a legit integer as output. So an analysis with the TrustInSoft analyzer would not raise a problem. It's different for the second case below, where it's the same function, except that the input is an integer and the output is an integer. Okay, in that case, it's likely that traditional tests will be happy, they will succeed, because if you provide a particular input, the input plus 1 is returned as an output. Okay, so it's likely that test will pass, but the TrustInSoft analyzer will complain that there's an undefined behavior in this implementation. In particular, in the case where I pass the largest integer as input, I will not be able to increment this value by 1 without causing an integer overflow. So you can see by those two simple examples the difference of approach of the two and how they are complementary, by the way. Also, I explained that the formal methods and the TrustInSoft analyzer in particular allows to feed the equivalence of billions of input values for the software that you want to validate. Okay, so you may wonder what's the positioning of the analyzer compared to fuzzing. That is a pretty well-known techniques, in particular in the security space. So just as a reminder, fuzzing provides the ability to test software with millions of inputs in an automated manner. It's a great tool to increase structural code coverage. By feeding different inputs, you are likely to exercise a different branch of code and also to detect some kinds of problems in the code. For that, you need some function that's called an oracle that allows to determine that something happened in that particular with that particular input that is interesting. Something that happened being a failure or a weakness that might be has to be fixed or might be exploited if left as is. Okay. Fuzzers are particularly used in security-sensitive contexts because they allow to find vulnerabilities, and therefore, when you have a security concern for your code, it's quite interesting to use fuzzers for that. We'll see that the formal method and technical proof goes beyond what fuzzers can do, but by no means we say that it should entirely replace fuzzing. If you're already use fuzzing, it's completely complementary. You can integrate the analyzer with any fuzzer. If you use AFL, American Fuzzy Lab, that is one of considered one of the best general purpose fuzzer on the market, then the TrustInSoft analyzer has out of the box integration with the fuzzer. So using both in conjunction is very easy. So if you're already working on the security of your code, you might have already used technologies like fuzzing to detect vulnerabilities in your code. And you may wonder what's the difference between fuzzing, whose general principle is to try millions of inputs on your code, this formal method. So let's first speak about fuzzing. In terms of security, already the good part is that security researchers use fuzzing to detect vulnerability in software by trying a large number of random or pseudo-random input values. Okay, so that's good. The bad part is that this is really time and resource consuming. Fuzzers needs to run for hours, days, if not weeks, to try those millions and millions of inputs. So it takes time to run a fuzzing campaign, time that you may not have at your disposal at any point in time in your development process. The second part is that fuzzers, they may miss undefined behaviors, they miss robustness problem if there's no obvious manifestation of the problem. And typically when you have something like a buffer overflow, you don't have an immediate crash of your code, you don't have an immediate visibility that something wrong is happening on the code, and the fuzzer may miss the problem. And the worst part, the ugly part, is that fuzzers are not only tools that are used by security researchers, by your own company if you do, but they are also used by cyber criminals. So if they are capable of using better fuzzer or better fuzzing techniques than you do, they may outsmart you and be able to find problems that you were not able to find yourself through fuzzing. Okay, so we'll see that fuzzing obviously is a good technology, and I encourage everyone to use it, but the formal method can let you go beyond fuzzing with exhaustive input testing and much faster than what you can do with fuzzing. So I stated that fuzzing has some limitation, and I wanted to give you an example before we wrap up this section on fuzzing. If you look at the code on the right side here, function that calculates something, but what it does doesn't really matter. As you can see, there's a divider that is computed as 1732 times x minus 7333 times y, x and y being inputs of the function. So if you test this function with a fuzzer, you are very likely to never find those values that could cause a division by 0, because the value computed is used as a divisor. Okay. Right now, as you can see from the function, the inputs have to be between 0 and 100,000. Okay, you may provide a few seeds. Typically, when you test in a good way, you immediately try values at the boundaries or near the boundaries. So you may want to try -1, 0, +1, and also 99,999. 100,000, 100,001. So to make sure that around those boundaries, you don't have values that can cause a problem. But in that particular case, and even if the code is naive, it's a good representation of a real life situation. The value that can cause a problem are not around the boundaries. They may be sometimes, but they are not always around the boundaries. And there's no chance that the fuzzer can find the value that, or very little chance that they can find a value that would cause a division by 0 in that particular case. Already with x and y being in the range 0 to 100,000, that's 10 billion possible inputs. So the fuzzer cannot try them all one by one. I would say typically the fuzzers allow to test 10 billion. 10 million or maybe 100 million inputs, but nothing above that. So you are unlikely with a fuzzer to find the values that cause a problem in that very simple example. And conversely, or in the opposite, with the generalization of formal method, you are certain if you say x can be anything between 0 and 10 and 100,000 and y the same, you are absolutely certain, there's mathematical guarantee that the analyzer will find that there is at least one value pair or one input vector that can cause a division by 0 in that case. So again, formal method and the TrustInSoft analyzer goes beyond what to summarize on fuzzing, fuzzing is an excellent technique, but it has some limitation, and those limitations as well are well addressed by formal method. One first limitation that I didn't mention in my quick overview of fuzzing earlier in my slides is that fuzzers, they will typically run on host, meaning that in the context of embedded software, you don't run the code on exactly the same execution environment as the one it will run on in production, and therefore problems specific to the embedded target execution will be missed or are likely to be missed by a fuzzer. Second thing, I touched upon this already, is that fuzzer with their pseudo brute force approach allowed to test million, tens of million, hundreds of million potentially of inputs, but not the enormous input space that can be performed or achieved with formal methods, which can be 10 to the power enormous numbers, as you've seen earlier in my presentation. Trillions of input value is not a problem with formal methods. And of course, with fuzzers, if you want to test very large number of inputs, you have to cope also with the execution time. Okay, it takes a lot of time. So if you want to integrate this in CI, you have long waiting times, etc. So it creates a lot of difficulty due to the difficulty. to the duration of the test. And finally, probably one of the most important problems is problem detection, because as I mentioned, fuzzing does the equivalent of traditional testing, and if those tests do not create an immediate manifestation of a robustness problem, the fuzzers are likely to be blind to the problem and not detect the problem. As I said, a buffer overflow will corrupt memory, but will not necessarily immediately crash the software or hang, which are often the manifestation that the fuzzers expect. And because of that, maybe fuzzers will miss the problem. This is not the case with formal method, where any problem, even if there's not an immediate side effect, will be detected. So I touched on this a little bit earlier. I said that one of the specifics of embedded software development is that the code will run on particular target, and this poses a particular challenge with static code analysis and testing tools. I would say in the world of tests, this has already been quite well addressed, but not yet in the field of static code analysis. So why or where formal methods really play or really shine the most? It's in critical software. Critical for two possible reasons: either critical by usage, meaning that a malfunction in that piece of software can have dramatic, for example, safety impact. If there's a problem on a nuclear reactor, on an airplane, or even in an autonomous driving car, life could be on the lines, etc. So for this reason, the software is critical. There's also another domain where formal methods are particularly useful. It's for software that are critical by volume. Probably if a mobile phone malfunctions, nobody will die, okay? But because of the size, the number of devices, the attack surface that it can cause, and the harm it can do in terms of reputation, in terms of financial damages, etc., one can consider those markets, let's say the market of IoTs in general, also a critical software market, because especially for security, a vulnerability in that space can have enormous financial implications. So in practice, all the code that we have seen here is mostly written in general in C++ code. There's also a piece of ADA in avionics for sure, but in the current case, this is something that is not addressed with TrustInSoft. You may find also other tools based on formal method that offer the similar capabilities for ADA. And this is software that is relatively low level embedded software, stuff like bootloader, hypervisors, OS kernel module firmware, routers, microcontroller, secure element smart meters. Okay, it's environment where the execution target execution environment can be diverse. Can be x86, which would be the most common, similar to a traditional computing host, but also often ARM, Spark, RISC-V, and more PowerPC, etc. All those environments have different characteristics, the size of the words, and more. Okay. So formal methods can be used for any kind of software, but they particularly shine in this space where the level of accuracy and exhaustiveness of the analysis is even more important than for traditional software. So what's so special with low-level code? From our experience of the market, two things. First of all, the two chains and the target architecture. And secondly, the memory layout. And we'll get into this in more detail. So in terms of target architecture, explain. There are different types of CPUs, they have different word size, the indenness can be different, the memory alignment properties are different for pointers, for structures, etc. And if you don't take all this into account in low-level embedded code, you are likely to not analyze the code as accurately as it should be. Okay. The second parameter is the toolchain. When you compile your code with particular compilation options, particular location for includes, macro definitions, and constant, this has an impact on the resulting code, and being aware of all those parameters allows to have an extremely precise emulation of the code as it will run on its target. Okay, let's take two examples of this. So for the first function, double dat, it returns the double of an input integer. Okay, and depending whether the long type on that particular target is of the same size as the int type, or if it's bigger, let's say int around 32 bits, long around 64 bits, this will work like a charm for any possible inputs. If longs are also around 32 bit, then you have a potential for an integer overflow, because if you pass a large enough input integer as output, you may have a long value that will overflow. So that's an example. And for example, if I call double dat with the value below, the exa value below, if I don't know the specifics of the target, and if I don't take that into account in the analysis, I cannot really tell if this will cause an integer overflow or not. The second example here is slightly more complicated. It's about Indianness. So I have a function MSB that performs, that provides the first character on 8 bits of a short. And if I call it with 0x beef, depending on the Indianness, as output I can get 0xBE or 0xEF. And therefore the value I can only determine the value of the variable C and its usage for the next statement, depending on whether I know the Indianness of the target or not. The memory layout, quite important when you speak, and that's where formal methods are particularly well suited for low-level code. For high-level code, you access the low-level physical components of your target through an abstraction layer. The memory layout is more or less completely abstracted, and the code does not really need to worry about any specifics of the memory layout. When you speak about low-level code, that's completely different. Okay. Custom low-level code or OS components like drivers, RAM controller directly access the physical hardware layer. The memory layout is not abstracted, and the physical memory location of data might be specific. So you may have address that are specific for I/O or for interfacing with physical hardware. And being aware of this when analyzing code is often quite important for precise analysis. So all this is well covered with the TrustInSoft analyzer. It's on the fringe of formal methods, I would say, but as a wrap-up, you can be completely aware of your target, and you can even configure the physical memory location of a particular memory area, and have an aware analysis of the code taking into account this physical memory mapping. So now let's move to industrial examples, and let's take the example of the Baidu Apollo self-driving library. So it's an example coming from the automotive. Baidu is a vendor in China that has developed a self-driving library, on top of which you can develop self-driving application. It's a library that's written in C++. And in the case of the TrustInSoft analyzer, we put our focus on the PNC map class and all the dependency class that models the vehicle position and all the surrounding object position in space. It's a total line of code of 300k lines of code, so it's a fairly large code base. Before analyzing with formal methods, of course, it was let's say, validated with traditional testing. But the drawback is traditional tests could only verify absence of software misbehavior, and could say undefined behaviors for a particular position in space of the vehicle and surrounding objects. So it's as presented on the bottom left part of this slide. And when it started being analyzed with a TrustInSoft analyzer, of course, we use generalization, and we modelize all possible position of the vehicle and all possible position of surrounding objects, pedestrian, red lights, road signs, etc., and verify that in none of those situations the vehicle autonomous driving software could have unexpected or undefined behaviors. Okay. What's interesting also with this example is that, of course, position in space are not modeled by integer. I spoke a lot about integer before, but it was just for simplicity of the examples, but it worked just as well with floating point value, as well as any other data types that are available in C or C++ code. So structures and also other complex type pointers, function pointers are all well supported for the analysis. The second example I will give is an example of an accelerometer. It's an example coming from the automotive, an accelerometer that is used as an embedded device for the automotive industry, and from ST Microelectronics. The code is open source, so for us it was easy to have access to it. And quite impressive result is that in 1 hour and a half we were able to detect a buffer overflow in the code of that accelerometer. Okay, we're starting from a situation where we did not know anything about the code, so this 1.5 hours is also the time to discover how the code works, to find a way to analyze it properly, and obviously to find the buffer overflow. But that's the final part that took only a few seconds or a few minutes from the hour and a half. Okay, after this problem was fixed, and you have a reference to that issue on the public GitHub repository, the TrustInSoft analyzer through its formal method engine confirmed that for all existing inputs defined by the existing test, whatever the registers in the hardware and the driver has no undefined behavior. That last example is also quite interesting. It's an analysis of the driver of the Goodix GT915 chip that is found in a popular touchscreen, popular mobile phone to control the capacitive touchscreen of the phone, in particular Lenovo and Wiko. It's also applicable for probably with limited changes to the automotive industry, where now everyone has a screen. It's a touch screen. It's in its car, and with formal method, it was possible to modelize the hardware for a particular configuration, and to simulate through the driver what would happen if a hacker, or to simulate what would happen if the screen would be touched with up to 256 fingers, which was the maximum the driver would allow. With physical tests, that's probably quite difficult to do. With TrustInSoft formal method generalization, it was really easy, and to make sure that in those probably unlikely in the condition, but condition that can be deliberately provoked by a hacker, the driver was robust and would not have any vulnerability, and this was what was confirmed: absence of undefined behavior and driver's immunity to a large family of security weaknesses. You can see all the CWEs that refer to what we proved. Last example, I forgot this one, the ARM embed TLS example. Interesting because it's related to security. ARM embed, formerly known under a different name, Polar SSL, is a widely used TLS library that is now under the ARM umbrella. And it was validated with the TrustInSoft formal method, both in terms of technical robustness and also for some part on functional proof. Okay, several issues were detected, notably some sign integer overflow and invalid pointer arithmetics. And same thing, after all those problems were fixed, we established mathematical guarantee of absence of vulnerabilities for a large array of CWEs. Okay, this achievement was hailed by the NIST in a report to the US White House, where you can see in a quick extract, TrustInSoft proved the absence of a set of CWE classes in Polar SSL. And generally, this report also mentioned that formal method is a good way to achieve extremely high validation of software at a lower effort than, let's say, traditional testing. Let's speak about the link to regulation and standards. In the safety space, standards have been around for a long time, and I would say that's where formal methods come from. Aeronautics with DO 178C, Automotive with ISO 26262. Those standards are very process-oriented, but it's quite interesting to notice that they all recommend formal method as a way to achieve compliance, especially for demanding safety or security levels like ASIL D for automotive or DAL A for aeronautics. In the space of security, that's a bit different. The landscape is different. Standards are only emerging for security. In the automotive space, the first version of the ISO 21434 has been released, but you can feel that there's not the same level of maturity as the 26262. And also, besides standard, there's let's say a government regulatory compliance with the 2021 US Executive Order around security, and something relatively similar in Europe in 2022 with the Cyber Resilience Act. All those things mandate a certain level of process, security by design, and a secure development lifecycle description as a means to ensure some level of security. So in all the safety world, standards are there since a long time, and we can see that more and more there are an equivalent standard emerging in security, even though in terms of maturity in general, that's lower. What's different between safety and security? Well, and why probably more and more people worry about security, even outside the traditional industry where safety was important, is that in safety, the world can be considered as indifferent. Problems in your code are hit accidentally, either because of a hardware malfunction, extreme operating conditions, or electrical glitches, stuff like that. Whereas in security, one can consider that the world is hostile, meaning problems in the code are hid deliberately, they are searched by cyber criminals, and it will only take time before they find your code weaknesses and find a way to exploit them. So what is accidental in safety becomes deliberate in security, so one can say that the problem is even worse in security. In terms of standard in security, I mentioned it already, but the maturity is not the same as for safety. And I would say right now the link between safety and security is not so obvious. Nevertheless, you can see that in the ISO 26262, there are brief mention that safety should be coordinated with cybersecurity, and ISO SA 21434 has been released as a complement to ISO 26262 safety. That said, it's still, this version of the standard is still quite light, under-specified, in my opinion. And yeah, for the moment, practically how to use this standard isn't clear. Probably, my guess is that there will be new version that will bring more details on what to do to achieve security compliance in the automotive. In the meantime, CERT is often used as a practical reference on what to do on software, what to check on software to achieve a certain level of security compliance in the code. The CERT is a standard that's issued by the Carnegie Mellon Software Engineering Institute. It's focused on security, unlike maybe MISRA, etc., that were in the past more safety related. There are both rules and recommendations. Rules is what should be enforced in your code. Recommendations are best practice that are recommended. Okay, and those rules, typically, if you compare to MISRA, in average, they tend to be more complex, and in particular, more complex to verify with static code analysis. Okay, I would say that with a traditional static code analysis covering well at least the high severity rule of the CERT is almost impossible, and this is proven by a quick benchmark that we did between the TrustInSoft analyzer and other static code analysis of the market, mainstream one. As you can see, even with TrustInSoft, we don't cover 100% of them, only 76%. But yet, we have a relatively significant edge and a number of more rules that we can cover than with those two other traditional tools that were around 40% of rule coverage. Finally, I said that those tools must be democratized. Formal method must be democratized. They also have to integrate well with development workflow. So part of this democratization effort and part of this this effort to become mainstream, there were a few things that were needed in those tools. Not related to formal method, but nevertheless necessary to integrate easily in those workflows. And that's the case with the TrustInSoft analyzer. Now you can find very exhaustive reporting capability with, in our case, a summary of the analysis, the details of each alarm that was discovered, also information on structural coverage with both function, line, statement, and even MCDC coverage for standard requirement for extremely high safety or security requirement. MCDC sometimes asked, and this information is available in I would say mainstream standard HTML for humans for readability. That's what you're looking on the right side. But also JSON CSV for machine processing. That's typically easier to process. In terms of continuous integration also, I would say continuous integration is something that is, let's say, a standard in a standard software development, but now is penetrating the world of embedded more and more. So having tools that can integrate in CI is also quite important. This is completely possible now, at least with the TrustInSoft analyzer. And then here you have an example of a Jenkins execution where the TrustInSoft execution is run as part of the CI, and that's it provides also the results are easy to process. You have an example here. The results are stored directly as part of the CI, so after the fact you can consult them. Okay. And finally, you can adapt your CI process and take a decision in the CI based on the result of the analysis. In that particular case, you have a build number 9 where the code was analyzed, and at the end, a check on the absence of undefined behavior is negative. Some undefined behavior were detected, so you can take the decision to fail the build and reject the code if that's the case. And then when you rerun after the fix, which is the case, the subject of build number 10, you can see that the check is positive, and therefore you can proceed and release the code if it's functionally ready. So this is a wrap now, and as a takeaway, remember that now formal methods are mainstream. It provides all the characteristics of a traditional static code analyzer in terms of usability. It provides, unlike those tools, unmatched depth of analysis with formal proof or functional proof, technical proof of absence of undefined behavior on your code. Okay, and beyond using those tools for compliance because it's required by standard, it provides an excellent level of validation. It can help you reduce your validation cost and your testing cycle. It's particularly well suited for software with high security requirements due to this mathematical guarantee. And from our own business, I would say it's something that is proven and to be completely industrially usable and successful on a wide variety of embedded software from aerospace, automotive, and IoT. This is it. If you are interested to know more about formal method or the TrustInSoft analyzer, feel free to contact me. You have all my details on the right side of that slide. Thank you for everyone, and I hope that you will enjoy soon the usage of formal method and its value.